start this morning's session. So, the speaker this morning is Marino. It is the first lecture of 3 on localization and project.
Okay, thank you very much. I would like to thank the organizers for the invitation to come to Stockholm. So I will talk about localization of large chain and essentially localization methods in the study of 3-dimensional chain and matter theories. I have to say, first of all, that I wrote some lectures which you can find on the net. So, and the lectures are largely based on these lectures. Localization, etc. This is, I think, I don't know the number here, but you can find it on the net. Okay, so there is the goal. There is like a short, a very concrete goal of these lectures. So it will be like a kind of guide for the rest of the lectures. So my goal is to look at ABEM theory. If you don't know everything I'm telling now, it will probably become clear later on. My goal is actually to prove this formula for the large and behavior of the free energy of ABEM theory. So a large formula. So this is actually a very beautiful test of ABS-CFT correspondence. It's a quantity you can compute in gravity and gives you a prediction for the gauge theory behavior strong coupling. And actually using these techniques of localization, you can actually do the calculation also in the gauge theory. Okay? So this is going to be my short goal, okay? Kind of very concrete goal. But of course, in the meantime, we will learn techniques to actually solve these problems, and in particular localization. Okay, so very roughly, I will first review a little bit gauge gravity dualities and ABEM theory. So this will be probably the content of the first lecture of today. And then my second lecture will be mostly on how to do localization, which is a technique to compute exact quantities in gauge theories. And then I will actually come back to the calculation of the free energy. So what will happen is that the localization is a technique that allows you to write the partition function of the gauge theory in a simpler form. That doesn't give you this result immediately. Once you have the result of localization, still you have to work out to find this answer, and this is what I will do in the third lecture. Okay? Very good. So let's start then with the dualities. Well, a characteristic feature of non-abelian gauge theories is that the long distance physics is very different from the short distance physics. And essentially, physics at strong coupling is very different from physics at weak coupling. So this is one of the main problems. For example, if you are doing QCD, you know that weak coupling, the degrees of freedom that you see in the Lagrangian are quarks and gluons, but at the strong coupling you don't see that. At long distances you actually see pions and things like that. So what we're going to address after in these lectures is a similar phenomenon, but of course in a much simpler setting, which is for these ABEM theories. So one of the things that people found is that at the strong coupling, the number of degrees of freedom scales like n to the 3/2, but with coupling, the number of degrees of freedom scales up to the square. This is a kind of very simple example in which you can see that a gauge theory has very different behavior in an important quantity at the strong coupling and weak coupling. This was found using ABS-CFT, and this is something that you can actually compute that. This is a weak coupling calculation. We'll review this. And the question is how you can go from weak coupling and strong coupling and find what are called interpolating functions that explain that the weakly coupled theory, as determined the coupling, actually displays this non-trivial behavior which you only see as strong coupling. And this is going to be one of the goals here. Okay, so of course when you want to do weakly coupled theories, you can do perturbation methods. So you have to be able to see perturbation theory. And what I'm going to do now is kind of very quickly review perturbation theory and the one-over-n expansion, which are the ways that we want to think about gauge theories in this case. Okay? So I will denote my gauge coupling like this. So it's going to be denoted by ES in these lectures. And the kind of theories that you can consider, I will write a Lagrangian very abstractly. So something like this. So you have a gauge connection. Then you have a differential operator, which can be first order or second order. So I write it rather with a D, but this can. And then I will have some sort of coupling in Q. So this kind of cartoon way of writing your Lagrangian. So as you will see, this way of writing it is not very convenient for Jan-Mills, but it's very convenient for machines, so we'll be interested. So if you have, of course, if you have Jan-Mills, you can write it like this. And here, this operator is of second order, it's a second order differential operator. You definitely have a cubic coupling, that usually represented like this, with a ds, and you also have like a fourth, you also have like a coupling, a four vertex coupling coming from here. But I'm not going to be interested actually in this kind of theory. I'm going to be interested in a theory which is called Chern-Simons theory, which is also an interacting theory based on a connection. And Chern-Simons theory is very similar in many senses to Jan-Mills, in the sense that you can write your Lagrangian in this way, and then you write it in the way that, or your action, so all these actions of Lagrangian. So the action of Chern-Simons theory, and we'll write it like this. So this is the gauge theory I will be interested in. So A here, so N here is a 3 manifold. I mean, usually when you look at gauge theories, you do 3 or 1. But actually, as we will see in these lectures, it's very interesting to consider a generalization of computing gauge theories on more general manifolds. A is a UA gauge connection. I will, by default, I will use in these lectures UN connections. And then here, one peculiarity of this action is that it's written using only differential ingredients. You don't use metrics to write it, so this is the wedge operator, the standard wedge operator of forms. Remember that the gauge connection can be written as a one form, and be thought as a one form. And D is the run differential. So dA gives me a 2 form and multiply by a 3 form, and I can integrate it without using any method. Okay? The same thing here, you have 1 form to the cube, so a 3 form, and then you can see that this metric, this action does not involve the metric. K here is an integer. So you see that the coupling is quantized. The reason for that is that I won't explain every detail here, but the reason why this is quantized is that you can see that this action is not invariant under large gauge transformations. So you want its exponential with the I to be well defined, you have to impose some quantization of the coupling. But in a sense, what I will do in these lectures is to look at this action as a standard action for a connection. So I have here a kinetic term, and here I have the type of cubic coupling that also appears in Jan-Mills. So I can, for example, do perturbation theory and do calculations in perturbation theory, and you see that the coupling here, the analog of this coupling here, that in Jan-Mills theory sometimes you write as G squared Jan-Mills, here is 1 over K. So perturbation theory will be good when K is large. Okay. So I'm not going to, this theory as a quantum field theory was studied by many people, like by Dresser and company, and also by Witten, was notably by Witten, who actually was able to find the exact non-perturbative solution of the theory. What we will do here is to use this as a building block to construct conformal P theories in 3 dimensions. And you can see already that the fact that this theory does not involve the metric on the thematic already guarantees that it's invariant under under scale transformation, so immediately under any diffeomorphism, because it's purely topological. So you can actually see that any change in the metric is not going to change this action. It's not clear how this is going to be maintained in the quantum theory, but you can see that up to some certain this is maintained. So it's a very good building block to start constructing conformal field theories, and this is actually one of the uses that Charles Anderson was put for more recently. Okay, so of course, you can work with this axiom in perturbation theory. Also, Witten found the exact solution of this model. If you didn't know about that, you could study this axiom in perturbation theory in the same way that you study Jamil's axiom in perturbation theory. But if you are interested in perturbation theory, in going beyond perturbation theory, you have to use some other approaches. And one possible approach was the one over an expansion proposed by Clark. So essentially, if you have a U-engaged theory like this, you can actually expand observables in powers of 1 over n. And this gives you an alternative way to actually think about the expansion. This is different from the perturbative expansion, and we'll see also is closely related. Now, in these lectures, the observable I will look at is actually the partition function of the theory. On a 3S theory. So what does this mean? Well, this means that you have to take your quantum field theory, you have to put it on a string. If your theory is conformal, you will have to couple it conformally to the metric. And then you just study quantity here, which is just an integral. And actually, we will study the Euclidean partition. So you have to take your quantum field theory, do a Euclidean continuation, put it on a curved manifold, and then compute this. So this is the action. Now, actually, this in perturbation theory is very simple, because this is just exponential of the sum of bubbles. So, of connected bubbles. This is the kind of thing that you never do in quantum field theory, usually, because you always divide by the partition function to normalize, so usually you look at disconnected bubbles, you don't look at them. But if you do, for example, thermal field theory, you have to actually compute these bubbles, because thermal field theory is calculating the partition function not on S3, but on Rn minus 1, so the thermal theory you study it in the manifold M or n minus 1 times the thermal circle. So you are not at, it's not that strange to calculate partition functions on core manifolds, and this is actually what you do in thermal field theory. So this is the kind of thing that you do like this. So this is one diagram that you have, and you can have this kind of diagrams. If you have this kind of vertex, these are the kind of diagrams. Okay. Okay. So what actually Toft pointed out is that you can actually reorganize these kind of quantities. Of course, here you have it's very convenient to actually think about the free energy, right? This is just my conventions are a little bit at odds with the literature, but I will call the free energy the log of the partition function of the state. I mean, many of these things will become concrete later on. For example, we will actually compute this free energy at one loop in the AVGN theory. So right now I'm just reviewing things. If this is not concrete enough, wait a little bit, and then maybe you can complain and we can go back. But for the moment, let me just give you kind of the basic ingredients. Now, what you can show is that in the 1 over n expansion, this guy has an expansion of this form. E of lambda, and here lambda is the so-called Toft parameter. And you can find a common common definition as ds times n. So, for example, for Young Mills, this is ds squared Young Mills n. And for this type of Chern-Simons theory, in which the ds is 1 over k up to factors of 4 pi that you can choose or not to include in your definition. So we'll see that the top coupling here is going to be n. So this is the common top coupling. And diagrammatically, it's very clear what this guy is. So LG of lambda is the sum of connected bubbles, connected double line bubbles of G minus G. And essentially what you have to do in order to get this double line sum is actually to thicken the lines of this diagram, and you will get different diagrams according to the way you thicken it, but the precise rules are, I mean, I assume you are more familiar with this, but if you have questions, maybe after my talk, we can discuss it in more detail, this sort of basic thing. So, for example, if you compute the G nu 0, so these objects here are called the G nu G free energies. So the G nu 0 free energy is the sum of the connected double line bubbles of G nu 0. So, for example, if you just thicken the diagrams without twists, you will get, for example, this sort of diagram. This is a diagram that contributes to this, and you also have this sort of double line diagram. Notice that each of these diagrams have a number which comes from doing the Feynman integrals, and then it has a power of lambda. So, for example, this guy here has just a single power of lambda. This guy here has a power of lambda squared, and so on. And you also have, for example, a genus 1. The first contribution you will have here will be this diagram, but with twisted lines, or something like this. So this would be the first contribution, and this is also a power of lambda. So you see that, for example, this standard diagram in the standard perturbation theory gives you two different diagrams in the 1 over n expansion. One goes like n squared, because all these guys go like order n squared, while this guy goes only with order n. Okay. Yes?
So these twisted diagrams, are they allowed in UN?
Yes, absolutely. So essentially the rule is that if you have this vertex, when you go to UN, you have this kind of, you have this rule in order to resolve the vertices. Okay. So this is the rule, and then when you use this rule at every vertex of these diagrams, you will generate this guy here and this guy here coming from here and so on. Okay. They are of course perfect. Actually, in a theory where there are no, all the fields are in the adjoint representation, the rules for the one over the rules for UN and for UN are essentially the same, because the UN factor decouples completely. Okay, so you see that in general you have the following structure. So this is a way of reorganizing perturbation theory. You see that order by order in n, yes? No. Order by order in n, you have an infinite sum of diagrams. So in a sense, it's like reorganizing perturbation theory. You look at it perturbatively. And in general, what you have is that FG of lambda is a sum of coefficients. It's a sum of n, a, g, n, lambda, n. Okay? And you can see that diagrammatically what you have here is an expansion at L much smaller than 1. This is an expansion of lambda equals 0. So this is what you call a weak top coupling expansion. And doing an expansion at weak top coupling is very much like reorganizing perturbation theory. I mean, you could just compute these anode diagrams, but doing your perturbation theory, but then making sure that the group factors that you put for your diagrams are only the ones corresponding to planar diagrams. But this is essentially a way to reorganize the perturbation theory. So the weak top coupling expansion you can find pretty much by using a standard perturbation theory. Now, here I have been simplifying my life a little bit because this looks like an analytic series, but typically there are non-analytic terms. Coming from measure plus one loop terms. So this is something that you know very well from perturbation theory. You are doing perturbation theory, usually, you know, the one loop terms typically give you an overall factor in front of the partition function, and then when you take the log, you get some log of the coupling that appear. But starting from two loops, this is really a power series in lambda, okay? So sometimes, as you will see, we will find logs of lambda in the expansion, but this is just a one loop term, not a measured term. Starting at two loops, you have a power series in lambda. And actually, as I said, it's analytic. This is, of course, not at all obvious, but if the theory, I mean, the technical requirement is that has no renormalons, AP of lambda are analytic modulo these terms, but the full series is analytic at lambda equals 0. This is a very important thing, which is actually the basis for a strong weak interpolation with ADS theory. So what I'm saying here, well, okay. So what do I mean here? Well, what I mean here is that these coefficients, A, B, N, grow on exponentially. And not factorially. So not factorially. And this is in big contrast to perturbative expansions in standard quantum field theory. You do a perturbative expansion in quantum field theory, you just do the standard calculation in quantum field theory. Even in theories which have very good properties, you will have a divergent series, a non-analytic series. One of the nice, in the coupling constant, one of the nice things that Toft found in this one over expansion is that order by order in n, the functions you get here are analytic at lambda equals 0. If the theory has no renormalons, this means that there are no divergences coming from integration over momenta. There are no factorial divergences coming from integration over momenta. So this actually applies, this condition applies to, I guess it applies at the equal force and it applies to true cycle theory. Essentially, it applies to all the super conformal theories that you find in the ADS, I guess. Also, for example, the only theory for which I know for sure that there are no these type of registers, I know that this has been proved. For these other theories, I don't know if there is a proof, but I guess it's pretty much safe that this is the case. So this is, as I said, this is a very important property of quantities in the 1 over n expansion, and it's actually the basis for this strong coupling interpolation. Let me explain you why. So what you typically find, and this is something that, for example, we found in ABN theory, and it's very satisfying to see that this general expectation you can actually make it concrete. What you find when you look at these functions, when you look in the complex plane, what you find is that this function is analytical and equals 0, but will have just a finite range of convergence. In general, it doesn't have an infinite range of convergence. It's not an entire function. It has a finite range of convergence. So this is the complex lambda plane. And let me remind you that typically you are interested in the behavior of lambda real and positive. Here, well, you can always choose k positive up to a panic transformation. So typically you are interested in lambda positive. So what you get from analyzing the diagrams is a function which is well defined here. Now, typically, again, what I said is this is what you want, and what actually happens in cases is that there is a singularity in this function, but it's not on the real axis. So, for example, for ABGN theory, there is a singularity here in the imaginary axis. Okay. So this is supposed to be generic. But for ABGN theory, you can see that there is a singularity, and this singularity is actually the reason why the radius of convergence of this function is finite. This is usually the case. But then, what you can do, if you are lucky, is that you can actually analytically continue this function from the region where it is defined by perturbation theory to the region of large lambda. Okay? So you can actually do an analytic continuation here, because if you go through the positive real axis, you don't hit singularities. You cannot do that in the imaginary direction because you hit the singularity, but you can do it here. So you can do an analytic continuation. Lambda much bigger than 1, and this is this weak strong coupling interpolation. So what you have to do for these interpolations is you have to find an analytic function which on this neighborhood reproduces the sum of double line diagrams, but then has a unique analytic continuation to lambda big, and it is in this region here where you will make contact with ABS predictions. But there is, there is all this kind of machinery involved here. So, because as I said, this series has finite values of convergence. Okay, now. So the 1/n expansion was proposed by Toff as a way of going beyond perturbation theory, because his hope, well, there were two hopes here. One is that you can calculate these guys in a single strike by using some trick, and the second is that this object will capture most of the strong coupling features you want. Okay? But of course, already you see the first kind of goal is very hard, because naively again, each of these guys in a sense are better than standard perturbation theory. Still, they involve a resummation of an infinite number of diagrams. So it's not obvious how to apply this problem, how to apply this approach to the problem of solving strongly coupled theories. And as we will see, localization gives us a way to actually solve this problem. But for example, this problem has not been solved in QCD, of course. Okay? Now, so what I'm going to do now is really introduce ABGN theory in detail, and then, because it's the main theory we're going to study, and it's gravity dual. So this is more or less the kind of quantum field theory introduction. Are there any questions at this point?
Yeah, I have one.
Yes.
If you go to the strong coupling, then the expansion would be 1 over square root of lambda. I know an n equals 4.
Yeah.
You can't
Here, in this case, it's going to be like this. So I will write this in detail for ABGN theory. Yeah.
But it's, I know an n equals 4. It's not. You can't sum it up, right?
You can sum it up here.
In the expansion of 1 over square root of lambda, there's none. It's
Yeah. You mean that there is like a problem of resumability when you go.
Is this also true for ABGN?
No. For ABGN, it's actually very nice. You have this kind of picture very clear. Yeah. What happens in this? Yeah. This is this thing related to the mass gap in the sigma model and so on, right? You have this kind of exponentially small ambiguities. Yeah. This is something very funny, because I think what happens is that. But this is slightly different. What happens is that asymptotic expansion at lambda equal infinity is non-Borel somewhere, right?
Yeah.
But this doesn't mean that the theory, that the function is not analytic at the origin, right? It's just that the asymptotic expansion at big lambda is an asymptotic expansion. But this doesn't invalidate this. For example, the gamma function has a log of gamma function has an asymptotic expansion at large z, but it's analytic at the origin, right? So you know. This is more like an accident of the asymptotic expansion at infinity, I would say, in that case. But here, actually, I don't know if the asymptotic, the expansion that we find in ABL, the one that starts with 1 square of lambda is asymptotic or not, because it's the expansion of a hypergeometric function lambda equals infinity. Maybe it's also asymptotic. But what I'm claiming here is that at the origin this should be an analytic. Then what happens with the expansion at infinity? That's another issue. Okay. So let me then start. What should I do? Actually, this is probably okay. No, I want to put that one. So the main actor of this story is going to be ABM theory. This is a supersymmetric three-dimensional theory. So let me review also a little bit rapidly the basics of sushi, the ingredients of sushi in 3 dimensions. And if you want like more technical details, the kind of supersymmetry transformations and so on, you can find it in many places, including my review. Okay? So well, you have a first multiplet, you have the vector multiplet. This is just inherited from the vector multiplet, the standard vector multiplet in 4 dimensions. So here you have a connection in 3 dimensions. You have a scalar, sigma, and the luminous. And actually, let me actually remind here that I will mostly use Euclidean continuation of the theory. So in this Euclidean continuation, these guys are independent, and then you have an auxiliary field D. Now, these 2 guys come from the dimensional reduction of the 4D, where the whole thing comes from the dimensional reduction of the 4D multiplet, and this sigma is just the fourth direction component of the connection in 4 dimensions. Okay, and this guy is an auxiliary field, and as we will see, when you write the Chern-Mills multiplet, these guys are dynamic, but for the Chern-Simons multiplet, these guys are non-dynamic. So for Chern-Simons, for the supersymmetric extension of Chern-Simons, these are going to be also non-dynamic. These are auxiliary. Okay, so there are of course 2 important actions for vector multiplets in 3 dimensions. One is the standard supersymmetric Chern-Mills. So well, you get the standard thing, right? 1, 4, 7 mu. You get sigma, where D here, D. When I write it like this, this is the fully covariant derivative. It's covariant with respect to the gauge connection. And if you are in a curve manifold, it's also covariant with respect to the spin connection. And then you have like a kinetic term for the Windows, right? And there is actually another term that I'm going to write here, which is important in what follows. I will probably rewrite it later, but I want to rewrite it now because it plays a role. So you see that this is the bosonic case, and now how the auxiliary enters, well, usually you have D squared, but actually, if you put this multiplet on S3, this you can always do. You can put this multiplet on S3 in a way that conformal invariance is preserved in general. So what you get is an extra term here. This you can actually work out. Again, this is like a long exercise that would take me, probably more than it's actually useful. And actually, I'm not that enthusiastic about this kind of possibility exercises. But some people like them. But the question here is that if you are on a S3 of radius R, you will get this kind of coupling here. Notice that when R goes to infinity, this term disappears and you get the standard D squared term. But when you are on a 3S field, D and sigma combine together. Okay? This you can actually see from the construction of the supersymmetric action in 3D. And this will be important later on. Anyway, you see that the bosonic part is this one, and there is this standard kinetic term for the gluinos, and this is the standard Jamnius multiplet. We will use this multiplet actually to localize the theory. That's why I'm writing it here now, because, for example, the fact that these three guys are positive definite in Euclidean symmetry is going to play a role later on, okay? And the fact that you also have this shift coming from S3. Again, if R goes to infinity, so you go from S3 to R3, this term disappears and you get the standard coupling, okay?
Why isn't there a Yukawa coupling?
Sorry?
Why
Sure.
isn't there a
No,
Yukawa-
there are more terms here.
Okay.
I'm just writing, absolutely. I'm just writing the bosonic term, which will be the more important ones for me, and just this one to show you that this guy here is dynamical in contrast to Chern-Simons. Of course, there are various terms here, and I will just write the terms that I need for my concrete calculations. Okay, so now let's look at Chern-Simons, the supersymmetry version of Chern-Simons. So the supersymmetry version of Chern-Simons is also based on this vector multiplet, but the action is very different. Of course, what you want is the bosonic part is the same as the bosonic Chern-Simons theory, right? So let me write it here, supersymmetry version of Chern-Simons theory. Well, again, up to some nominal constants, so we can represent that later on. We get the standard thing here, so 2i over 3 a cubed. And now we'll have a term for the gluinos. We have lambda bar lambda. And then we'll have a term involving d and sigma. So you see here that everybody is auxiliary. Here, both lambda, d and sigma are auxiliary. So everybody's, except for a, is auxiliary. So actually the supersymmetric version of Chern-Simons is not a big deal, because it should be equivalent to the standard Chern-Simons field. You should be able to integrate all the auxiliary fields. And then this is actually equivalent to bosonic Chern-Simons field. This is actually a useful equivalence, for example, because as we'll see later, we should be able to solve this theory with localization. So the answer we should get for the partition function of Chern-Simons theorem S3 for this supersymmetric theory should be the same one that the one for the bosonic theory. This is like a consistency check of the procedure. And actually this is the case, because as I said, Witten computed this for us in 1989. So this is equivalent to bosonic Chern-Simons theory. Now, how do you get something new? Well, the way we get something new is by coupling to matter. Now, you couple this theory to matter, then it's no longer true that you can just decouple things. I mean, now things are coupled, and Chern-Simons theory plus supersymmetric matter will have a non-trivial dynamics. Okay. So for this, I have to introduce matter. So then this introduce the. What I will use again is again the three-dimensional reduction of the chiral multiplet. So I have here the chiral multiplet. And then phi. And this as complex scalar. Then you have terms which again are in the Euclidean, so they are independent. And then you have the auxiliary fields. These are the auxiliaries. And the Lagrangian for this matter theory is again quite standard. So you have phi bar, and you have not. These guys have terms. Okay, so this is everything we're going to do here is we're going to be based on vector multiplets of again usually of UN. Okay, so as again by default here it would be UN, and then I will use the supersymmetry Jamnius multiplet as a regulator, as you will see. But I will be interested in using supersymmetric Chern-Simons matter theory or supersymmetric Chern-Simons theory for the vector multiplets, and then I will couple to matter. Now, when you couple things to matter, as you were pointing out, there will be couplings between the matter fields and lambda, so you won't be able to integrate it out like this. So there will be a dynamic. Yes?
So the dimension of lambda bar is chosen is something
Sorry?
different. So in the Chern-Simons action,
Yes.
it doesn't have the, I mean, it doesn't have the same dimension as the lambda in the Young-Mills action. What are the dimensions of the lambdas? You know what I mean? Maybe lambda bar has to have.
But it should be consistent.
Okay, there isn't. So it's still 3 halves.
Yeah, I think it's 3 halves, right? Yeah, I think it's 3 halves.
So there is.
So let me just see what is the, yeah. It should be 3 halves, right? Yeah. So it is 3, right? So it's 3, right?
Okay, yeah.
I mean, notice that, yeah. Okay, so now how do you construct this abelian theory? So let me now write here. Now, concerning the dimensions, let me point out that here in these lectures, I will just consider theories where the dimension of the fields are just the canonical ones. So we have at least 3 supersymmetries, what is called n=3 supersymmetry. Now, in the way I'm writing things in the language of n=2 supersymmetry, right? But I will actually work with theories which have, well, abelian has actually n=6 supersymmetry. And you can generalize many of the things I will say, but only with the condition that the anomalous dimensions are the canonical dimensions are the anomalous dimensions, so there are no renormalizations of the anomalous dimensions. You can make a lot of these things also true for theories which are more general, but it's just much more complex. So in abelian theory, what you have to do is you have an appropriate combination of these guys. So the way you actually represent this very often is to a quiver. So you need 2 vector multiples to begin with. So we will have 2 gauge connections. So we'll have, let me call it A1 and A2. And actually, in principle, you can use different gauge groups for these connections. So these circles represent the fact that you have vector multiplets with super Chern-Simons action. So the dynamics of these connections will be derived from this Chern-Simons action. And now you have to add matter. So what you have to add now, you add are 4 chiral multiplets. In bifundamental representation. So this means that you will have fields. So actually, usually it's written like this. So you have 2 fields in the bifundamental representation. So the bifundamental representation means that you will have 2 gauge indices. You will have a gauge index A for one of the gauge groups in the fundamental and an index B bar in the anti-fundamental of the second gauge group. And then you will have 2 fields like this, and actually 2 fields in also divided fundamental by the conjugate one. Okay. So then you call this maybe I and J, so A goes from 1 to 2, and J goes from 1 to 2. So by fundamental representation, as I say, it means that it has fundamental or anti-fundamental with respect to the gauge group. So this will be, say, well, that depends on how you want to. Let me assume that these guys have the phi A B bar, and these 2 guys have the phi A bar B. Okay. But that depends on what is the meaning of the arrows. But this is the content. So very importantly is that they appear in conjugate, in complex conjugate pairs. This is going to be important later on, and there are 4 of them. Okay. So with this theory, with these ingredients, you can just write now the Lagrangian. You will now find, you can find this Lagrangian in reference. I won't need to write it in detail. But you will have, of course, action for the matter fields, action for the Wilson matter, and they will happen through lambda, through the gauge connection here, etc. So you have a complicated theory, complicated interacting theory now. So you have all the interactions that come from the Chern-Simons multiplets, which give you a non-trivial, by the way, the pure Mosollet-Chern-Simons theory already has a highly non-trivial perturbation theory. So it's an interactive theory. And on top of that, you will have all the interactions coming from the vertex with the matter fields and so on. Okay. So it's a sort of complicated theory, but it can be shown that if you add an appropriate superpotential for these fields, so for these fields phi A B bar phi A bar B, the theory is actually superconformal. You get a superconformal theory. The superpotential with is some right here, but it just involves coupling these fields. So it's something like F1 A B bar, F1 B bar, C D phi 2 C D phi 1 A, something like that. So that's completely. I think you can write it in this notation I'm using. You can write it here. So you have to use the four. You have to use the four chiral multiples here in this way. So there are two in the bifundamental and two in the anti-bifundamental, and you couple like this. And it was, I think, it was argued by Aharoni, Berman, Jeffries, and Mandazen in the original paper that if you add the superpotential, the theory is superconformal. And actually, I have never studied. Sorry?
You have 3 1s and 1 2.
Oh, sorry. So there must be something wrong here. So maybe this is the 2, right? Yeah, I mean,
I think he anti-symmetrized too.
yeah, symmetrized. Oh yeah. Actually, this is minus, right? Yeah, this is minus. Yeah, I mean, I'm not going to use this thing, so probably this is enough for our purposes. But just one. The only thing I want to mention is that well, this is a natural quartic combination that couples correctly the for example, the representation. So this here here you sum over the signs over the indices of the anti-fundamental. Here you sum over the indices of the fundamental, and the trace is actually also correct. Okay? So this is what I do here. Now, as I said, this theory was shown to be superconformal, and actually the basic thing that you actually did here is the fact that in bosonic Chern-Simons theory, the only effect of renormalization is the fact that K can have a shift. So, for example, depending on the degree of supersymmetry, for example, the purely bosonic theory has been argued that you have a shift of K plus N. But essentially, the fact that K is an integer, in order for the theory to be consistent, means that it cannot run in an arbitrary way. It has to be quantized if the theory is consistent. And actually, what people found in calculations that already bosonic theory only gets renormalized, K only gets renormalized by a shift. And you can actually see that if you have enough supersymmetry, thing n equal 2 is enough, then K doesn't even get this shift. This shift is cancelled by supersymmetric effects. So the K doesn't run. Already K cannot run arbitrarily because it has to be an integer. So renormalizations are just integer shifts of K, but if you have enough supersymmetry, it doesn't run at all. And this is the basic for the superconformal property of this theory. So already the basic idea again is this idea that I think is due to John Schwarz originally, that you have a Chern-Simons theory, the fact that K is quantized puts a big constraint on the way the coupling constant gets renormalized. So even if you couple to matter, the quantization of K is a very deep feature of the theory in order for it to be consistent, and then you won't be able to play around with the coupling constant in an arbitrary way. Okay? So So this is the basic idea behind this property.
But I mean, once you add matter, does K still have to be an integer after you add matter?
Yeah. Because you know the bosonic piece, already a large scale transformation of the bosonic axiom will actually already shift it.
Okay.
You cannot play with that. I mean, whatever you do in the matter thing, the bosonic axiom will be not invariant large scale transformation.
Even though it's not really topological anymore, right?
No, it's not topological anymore, but it's a property which is just part of the, it's just a basic gauge invariant, a basic non-gauge invariant property of the Chern-Simons axiom. So this goes. Now, one of the reasons why people study this theory is because this theory has a gravity dual. So let me use my last 10 minutes to more or less review this. So this is going to be a review. I'm not going to explain everything here. And actually, because first of all, probably I'm not the most qualified person to explain all these things. But also because my focus is more on the kind of base theory approach to the calculation. But of course, you know, one of the reasons why this theory was important is because it's supposed to be the world volume theory of n. So here, in principle, I use different ranks, but I will, for the rest of this talk, I will consider the case in which the ranks are the same. And let me actually, I mean, this is an important thing. There are two parameters in this theory. One is n, which is the rank of the gauge group, and the other is k, the coupling constant. Everything else, there is no other coupling in this theory. Okay? So this is like in n equals 4 super Yang-Mills. So the rank of the gauge group and the non-running coupling constant d squared Yang-Mills. So here we have the same. Now, the basic insight of these people is that this was the theory of n to branes on C4 mod 6K. So here you see the appearance of the interpretation of these parameters. Here n is the number of n to branes, and k is a purely geometric parameter. Just is a CK action on C4, which is this kind of orbital quotient by e to the phi I over k. And the interesting thing about this theory is that already in the original article by Maldacena in 1998, he actually noticed that when n is large, you can actually trade the M2 branes. This is the standard ADS-CFT argument. You know, the M2 branes are going to create a big bar reaction, but you can actually replace the bar reaction on the gravity background. So you get curved geometry with a flux. So the remnant of the brane is the fact that there is a flux. And this is actually a very nice geometry, ADS4 times X7. So X7 here, sometimes I will refer to X7 as a more general manifold, but here is S7 mod ZK. And so the ZK is inherited from this theory here. And then, you know, this actually is the famous vacuum solution of 11-dimensional supergravity that many people studied in the 70s and 80s. So the metric, these are going to be useful equations later on, is just the metric on A is a product metric here, metric on ADS4 plus the metric on X7. So L squared is the radius of the common actual factor of 2 of ADS4 and X7. Then, you know, there is a F is DC, so we are in the dimensional supergravity. There is a 3-form field, and its strength here is given by 3/8 L cubed of the volume form of ADS4. So this is the volume form of ADS4, and this is the famous Freund-Rubin ansatz. And actually, as an exercise, I think it's a good exercise that one has to do once in your life, and it's actually an easy exercise, is to actually check that this is a solution of the equations of motion of supergravity, of 11-dimensional supergravity. It's easy, and if you want to do it or you want to redo it, I mean, I can tell you what's the solution. Writing it down. So this is a solution of this the famous Freund-Rubin ansatz. So this is one of the nice things about ABN that actually makes contact with this beautiful old story about 11-dimensional supergravity. Okay, so here you have to tell me what is the radius, and the radius is actually related to the original number of degrees and the usual light. So you have n. The radius is of course related to the flux here. So let me write it this way. So x7, the Hodge-Dual of F4. So the Hodge-Dual of F4 in 11 dimensions is a 7 form, and then integrate is from over x7, which in this case is the sphere, and you get this relation. And this relation is actually only valid at large n. There are subleading corrections to this relation, and here LP is the 11-dimensional length. So let me now just compare before finishing. Just compare the parameters and make a dictionary. So I will use two pictures of this. This is another virtue of ABN theory. Since this is a duality with M theory, you have two ways of looking at it. You have the M theory point of view, and you have the Tie-2A theory point of view. So here I'm presenting the M theory point of view, making the relation to the dimensional supergravity. But just to summarize the dictionary, so there is a dictionary then between ABN theory and this 11-dimensional supergravity solution. So in 11-dimensional in M theory, we have two parameters. We have K, which is a purely geometric parameter. And we have the standard r-dimensional parameter, which is the radius of these objects divided by the Frank length. And we have to be able to relate this to Kn. But of course, K is K, so this is the gauge theory. K in the gauge theory is the K in M theory. So notice that this coupling constant is purely geometric. And finally, by combining these equations, you get this important relationship that we will use very often in these lectures, which is that n is related to this one. Okay, so it's L divided by L divided by K. This is just follows from this relation. It's an easy exercise. Okay. Now, as a final exercise, and then this is my last thing, it's after a useful exercise. Although I will give you the solution later on because we will use it to derive an expression for the 4-dimensional Newton constant. In terms of gauge theory. So since we have a compactification on ADS 4 times x7, we can think about doing some second-line reduction on x7. So we have a 4-dimensional theory, and it's a useful exercise to actually calculate the Newton's constant of the effective gravity in ADS 4 in terms of all these data. Okay, so as a function of k, because this will be very useful in order to actually write the strong coupling prediction for this partition function that we write about. This is what we do this afternoon. Okay. Again, this is a very easy exercise. If you really want to, I mean, I think it's good to do it in order to get some familiarity. And again, if you have questions, you can ask me.